Hi, this is Mike Stanczyk with Digital Electronics Classroom. In today's video, we're going to be talking about the parallel circuit model rules. And so these are all derived from the Kirchhoff's laws and Ohm's law. And we're going to see that using this simpler model of a parallel circuit model, we can use some rules that will be easier to use to analyze our circuits. So let's get started. Parallel circuit rules. Two elements are in parallel if they share the same two nodes. What does that mean? Well, let's draw a picture of a parallel circuit. So to identify the nodes of the circuit, I can box out all the areas that are not elements. And so if we box out all of the wire networks that connect the elements together. So something like this. And we can label these nodes as A and B, some alpha letters. And then what we see is that for the rest of our elements here, so let's call this V0, let's call this R1, and let's call this one R2. So for the rest of our elements, they share the same nodes. So they touch A and B, A and B, A and B. So a lot of times the rule here is given as that the two resistors must be side by side, and that can be a little bit confusing. This is more specific. It says that they have to touch the same two nodes. They don't necessarily have to be side by side or arranged to look side by side. They just have to be touching the same two nodes, and if that's the case, then they are in parallel. So let's start out with doing some of our rules. We'll start out with KCL. So KCL is the Kirchhoff's current law. So let's draw some arrows to represent the current direction. And so we have I0, I1, and I2. And so our KCL, if we go ahead and look at the node, look at node A, we would say that in is equal to out of node A, and the ones that go into node A are just I0, and the ones that go out of node A are I1 and I2. And so we can see by that expression that the two currents that are exiting the node add up to the current that's entering the node. And so this is the battery current, and these are the resistor currents. So we can say that the currents add. And that's our first simplified rule for parallel circuits. Now let's take a look at Kirchhoff's voltage law. So Kirchhoff's voltage law, to do that, we're going to have to do a loop. So there's going to be 3 loops that we'll do. We'll do that left inner loop, the rightward inner loop, and then we'll do a loop around the outside. And to do this loop, we have to give polarity symbols to our voltages. And I'm going to do it in this fashion. Plus, minus, plus, minus, plus, minus. So for the first loop, and maybe I'll label these just 1, 2, and 3. Okay, so for that first loop, what we have is a rise from minus to plus, that's a rise in voltage. So a rise of V0, and then when we go back down through here, we have a plus to minus, that's a drop across V1. And so V0 equals V1. Remember, this is that rises equal drops. This is Kirchhoff's voltage law. And so for the second loop, we have a rise through R1 and then a drop through R2. A rise because we go from minus to plus, a drop because we go from plus to minus when we go around in that clockwise direction. And so we have that V1 is equal to V2. And then lastly, around the third loop, we have the outside loop. We have a rise, minus to plus, through V0, and then a drop, plus to minus, through V2. So we have V0 equals V2. So looking at these relationships, they're all equal to each other. And so we come up with our second rule, and that is that voltages are equal. Fantastic. Now we're going to add in Ohm's law. And this is going to tell us a little bit about resistance, because Ohm's law includes V, I, and R. So I'm going to start with the KCL expression, I0 equals I1 plus I2. And then I'm going to substitute for Ohm's law, where I is equal to V over R. And that will give us V0 over R0, but really it's not R0, it's REQ, the equivalent resistance. Now if you need some reminder or refresher about the equivalent resistance, you can look back at the series rules video. And then this is V1 over R1, and this is V2 over R2. That looks great. But by KVL, we know the voltages are equal. So V0 equals V1 equals V2, so we can just call this some V, and we'll divide by V. So V is in every term here, so when we divide by V, we end up with the expression 1 over REQ is equal to 1 over R1 plus 1 over R2. And if we had more resistors here, we could just add in those resistors all the way up to our nth resistor. Okay. Now, how would we say this? We said that, the voltages are equal, the currents add to each other, but we didn't say, how do we say this one? You might say something like the reciprocal, the equivalent resistance is equal to the sum of the reciprocals of the individual resistances, but that's quite a mouthful. And actually, this comes from the fact that whenever you add another path in the circuit, when you add another path to go down, it makes the overall ability to flow easier. And we have a term for how easy something is to flow, and that is called conductance. So instead of just looking at the resistance here, we can look at a term called conductance, which just says how easy it is to flow. And that means the current. Okay. And conductance gets the symbol G, and it's measured in Siemens. And so conductance in Siemens, like so. And so it's G with the symbol for the unit being a capital S. And what we see here is that the conductance is the inverse of the resistance. And so if it's easy to flow, that means the resistance must be small, making this a large number if the denominator is small, right? And if it's hard to flow, that means the resistance is large, making this a small number because the denominator is large. And so that's the relationship here. So we can write 1 over REQ as GEQ, 1 over R1 as G1, and 1 over R2 as G2. And so this is saying that the conductances add. So the conductance is add. But most people like to remember the equation like this. And this makes sense because when we buy resistors off the shelf, they're not given by their conductance value, they're given by their resistance value. So when we want to figure out what an equivalent resistance is, we typically use that expression to do so. All right, let's look at one more thing. Let's look at powers. So power is V times I. So if I want the overall power delivered by the battery, it's going to be V0 times I0, right? But we know that the voltages are equal to each other, so these are all going to be the same. And then the currents add up. And so this is just going to be some V multiplied by I1 plus I2. And then if I distribute that out, what I get is V1 I1, because V is V1, plus V2 I2, because V is also equal to V2, all the voltages are equal. And so we get that P0 is equal to P1 plus P2. And so powers add. So just to summarize here then, we have powers add, currents add, voltages are equal, and conductances add, or 1 over Req is equal to 1 over R1 plus 1 over R2, dot, dot, dot. So this is our summary of everything that we've learned today, the parallel circuit rules. Well, I hope that has value for you and that you enjoyed that presentation. I'm Mike Stanzik with Digital Electronics Classroom, and until next time, have a wonderful day.